All right, so we're going to continue with uniqueness, but we're going to use it as a tool today. So, is Caleb here?
Oh yeah.
There you go. Look, someone sent it there. Okay. Okay. So let's do. So we're going to continue with uniqueness. But I want to show you guys how to use uniqueness to prove things. Okay, so in the previous class, we introduced a new symbol. We introduced a new quantifier. So it was this thing here, and it was there exists a unique. Okay? So I just wanted to remark that this exclamation point, we've been using exclamation points for not. This exclamation point has nothing to do with not. Okay? So I wanted to point that out. It's just a new quantifier that means there exists a unique. Okay? So sometimes we are given uniqueness statements. Uniqueness statements. And they can help us in the course of the proof. So sometimes I talked about what's a framework of proving a uniqueness statement. So now sometimes we will be given uniqueness statements, and they're useful. Okay. So okay. So the example that I want to do is the fundamental theorem of arithmetic. So recall. So p in the natural numbers with p not equal to 1 is called prime. If p divides a times b implies p divides a or p divides b. Okay, so here a and b are, say, natural numbers. The same definition can apply for the integers as well. Okay? If we were going to do it for the integers, we would say p is not 1 minus 1 or 0. Okay? For this thing here. Okay? So that's what we have. We're going to use this property a lot. So we'll suppose something is prime, right? And we'll have that it divides something, a product of two things. And that allows us to conclude this or this. Okay? So, and let me tell you the fundamental theorem of arithmetic. Okay? So there's a theorem called the fundamental theorem of arithmetic. Okay, so the fundamental theorem of arithmetic says every natural number has a unique, let's say every natural number greater than 2 or greater than 1 has a unique decomposition into prime powers. Okay, so this is the statement in words. So another way of saying this is that for all n in the natural numbers, for n not equal to 1, n is equal to P1A1, P2A2, PRAR, where P1 through PR are prime numbers, and A1 through AR are integers, or natural numbers. Okay, furthermore, the set of primes and the set of exponents okay, so the collection of primes and exponents, by that I mean the collection of primes and exponents. That's how you're supposed to parse this. Okay? The collection of primes and exponents are unique. So they uniquely determine the number.
Is that through addition or multiplication?
Multiplication. This is multiplication here. This is you multiply it like this. Okay? So let me give you an example. Okay, so here's an example. 1 is like 10 is equal to 2 times 5. Okay, and in this example, P1 is 2, P2 is 5, A1 is 1, and P1 is 1. Okay? So let's do another example. So, excuse me?
P1 should be A2. The bottom right.
Oh, yeah, A1, A2 right there. Yeah, exactly. Thank you very much. Okay. So that's one of them. So here's another one. So we could do, say, 150. Okay, so this is 15 times 10, right? This is 3 times 5 times 2 times 5. So this is 2 times 3 times 5 squared. Okay, so P1 is 2, P2 is 3, P3 is 5, A1 is 1, A2 is 1, and A3 is 2. All right, so that's what we have for this one. So what's the point of this theorem? The point is that you could maybe factor this, so you can maybe try and factor a number in 2 different ways, and you'd get 2 different factorizations, but you'll get the same thing. So let me kind of bring something really old back. So let's do 150, right? So, right, this could be 15 times 10, right? And then you could break this down into 3 times 5, and this could be 2 times 5. Okay? And another way you could break it down is that you could take 150, and this could be 2 times 75. This could be 5 times, or 3 times 25. And this could be like 5 times 5 down here. Okay, and so no matter which way you break this down, you're going to get the same factors with multiplicity. So it doesn't matter the order that you do this in. Okay, so the point is, how you factor the same factors. Every time. Okay, so that's the theorem. So we don't quite have enough to prove this theorem, but I would like to use this theorem as an example of a uniqueness statement. So the primes, together with how often they repeat, right, are the invariant of the number. Yeah?
So, like, say if we have, like, if we need to use it more, we don't have to prove this, we can just use it.
Yeah, we can just use this for now. Yeah. Yeah, and I just want to use it to be helpful. And so the numbers here are called the prime factors here. Those are called the prime factors. Okay, so let me give you another definition. So two natural numbers, A and B, are coprime if and only if they have no common factors. No common prime factors. Okay, so there's no common prime factor. Okay, so I'm going to talk about how to use this. Okay, so factorization and proofs. So this is a new little heading here. So that was like my little introductory thing. And now I'm going to give two examples. Okay, so let's give an example. So here's a claim. Okay, so the first, yeah.
Generally gone over this before. Is 1 a prime number? Or is it
No, 1 is a unit. So in the definition of prime, I explicitly excluded 1.
Okay.
So a unit is an element of a ring which has a multiplicative inverse.
So, but are we including it as a?
No, 1 is not a prime. We explicitly exclude 1 as a prime. 1's not a prime. It's a unit.
So, but for every natural number greater than 1, has a unique composition of into two prime into
Prime factors, yeah.
Yeah. So if you had like, so 2 is prime.
Mm-hmm.
And so it's only divisible by 1 in itself.
Mm-hmm.
But so to get 2, you would have to multiply 1 and 2.
Well, 2 is 2 to the, so there's one prime factor.
2 to the 1.
2 is 2 to the 1.
The 1 factor. Okay.
Yeah, exactly.
So write it down as 2.
Yeah.
The power of 1.
Yeah.
Thank you.
Okay, yeah, no problem. Okay. Other questions? Okay. So let's do this one. This one's fun. We're going to do two irrationality proofs. So square root of 2 is irrational. Okay? So this is fun. So proof. So how can I prove this, guys? What's the technique that we have? Yeah. Proof by contradiction. Okay, let's do that. Yeah. Yeah, suppose not. Okay? Then there exists a b in the natural numbers with b not equal to 0. Let's say, okay, I'm going to say this and I'll explain what it means. Coprime and b not equal to 0 such that square root of 2 is equal to a over b. Okay, so this is the supposed not. Okay, so I put them in the natural numbers here because it needs to be a ratio of positive numbers since this is a positive real number. Cool? Okay. I suppose that these two are coprime because if they weren't coprime, right, I could just cross out the extra factor that they had in common. Does that make sense? Okay, so if they had a common factor, well, I cross out that common factor. So, and this is a statement that we say, without loss of generality, we assume that the rational number looks like this, where these two numbers are coprime. Does that make sense? Does that make sense why I say without loss of generality? Right? It doesn't hurt to assume this because we could cancel if not. Okay, so we have this, and now what should I do? Square both sides. Why don't we square both sides and bring it over to this side? So this implies, so equation star implies the following, that 2b squared is equal to a squared. Does that make sense? Okay. So now, since 2 divides, so do you guys see that 2 divides a squared here? So this means 2 divides a squared. Okay, and so what I'm going to end up showing is I'm going to show that that these two things are not actually coprime, right? And that's going to derive our contradiction. Okay, so that's where I'm going with this. So 2 divides a squared. Okay, so the definition of prime, we said that if 2 divides the product of two numbers, 2 is a prime number, it must divide one of the numbers. Okay, so by the definition of prime, this means 2 divides a, since 2 is prime. Okay, so here we have a product of two numbers, but the two numbers just happen to be the same. So it's like 2 divides a or 2 divides a. Does that make sense? Okay. Okay. So since 2 is prime, so we can write a is equal to 2c for some c in the natural numbers. Do you guys agree with that? Okay, that's the definition of divisibility. Okay, putting this back into, let's label this equation, we'll call that dagger. Okay. Putting this into dagger, we get here 2b squared is equal to, and then we have 2c squared, and this is equal to 2 times 2c squared. Okay. So here, I'm going to use a property of the integers. Okay? I'm going to use a property of the integers which says that I can cancel the 2 on both sides of those equations. This is something that we haven't proved, but that I told you. Right? So this implies, since z has the cancellation property, and I'll explain what the cancellation property is again. We have, now I can just cancel the 2's on both sides of that equation. B squared is equal to 2c squared. Okay, so let me do a little thing here about the cancellation property. Okay, the cancellation property. Here?
It's like 2 squared.
2 squared. So we have 2 squared times c squared.
Oh, okay.
Right? Yeah. The cancellation property is the following. It says that if xy is equal to xz, so this implies that y is equal to z. Okay? And not every commutative ring has this property. Only special rings do. And those special rings are called integral domains. Okay? It's a little like fun fact. Okay? So, and we're using, this is one of the things we need to know about the integers in order to do this proof rigorously. But I'm going to tell you guys that this is true, and we'll come back to this maybe later. Okay? Okay. So since Z has the cancellation property, we have this. Okay? And what does this tell us?
2 divides b squared.
Okay, hence 2 divides b squared. And what must we have? 2 is prime, so,
2 divides.
and hence 2 divides b. Okay, so 2 is prime. So if 2 divides a product of 2 numbers, 2 must divide one of those numbers. The number is the same here, so 2 has to divide b. Okay, so we're using the definition of prime again, and the fact that 2 is prime. All right, so 2 divides a and 2 divides b, which implies, which says that a and b are not coprime. They share a factor of 2. Which is a contradiction. Of rationality. Cool? Okay. All right. So that's cool. So we proved that the square root of 2 is irrational. You guys can show the square root of lots of things are irrational now, using this similar proof to this one. Okay? So there's kind of a more general proof in this one where you can show things are irrational. Okay, so, all right. So let me do another proof now. Okay, that kind of goes along the same idea, same lines. Okay, so claim. So log base 10 of 3 is irrational. Okay, so I'm going to prove that this number is irrational. So here's the proof. So how should I proceed in this proof?
Start by setting it equal to r over b.
Yeah, let's suppose not, and we'll do another proof by contradiction. Suppose not. So this means we suppose there exists some a, b in the natural numbers coprime with b not equal to 0 such that log base 10 of 3 is equal to a over b. Okay, so we're doing this in the real numbers here. Okay, of course, we're assuming things like the log function and this. Okay, I just want to remind you guys that these are both positive because here, log base anything of 1 is 0, right? And that's the kind of breaking point between positive and negative numbers. It smells like it's burning again, right? Right. Okay. So we have a record of like when it starts burning because it's on video. Anyway, it's kind of weird. Okay. So now what should I do? Anyone have any suggestions? Yeah. Yeah, why don't we raise them both to the power of 10? Okay, so this implies, so now we're using the properties of logarithms. Okay, so in this proof, we are assuming properties of logarithms that 3 is equal to 10 to the a divided by b. Okay, we're also supposing things like square roots exist. Okay? And this in turn implies,
Is that like a slanted divide, or is that
this is a divided by b, right? That's what I mean. So it wouldn't be like, it wouldn't make sense if I did just the divide sign, because that would be like 10 to the true, right? We can't do that, okay? Or 10 to the false, right? It would be 10 to the false. Anyway, here, okay, we can raise both sides to the bth power. Okay, so let's raise both sides to the bth power, and we get 3 to the b is equal to 10 to the a. Okay? And now, what does this give? So now, we have a prime on the left-hand side, and then we have a product of prime, so a prime power on the left-hand side and a product of prime powers on the left-hand side, on the right-hand side. So 3 to the a is equal to 2 to the, or 3 to the b is equal to 2 to the a times 5 to the a. Okay, so this contradicts the fundamental theorem of arithmetic, okay? Unless a and b are both 0. So this contradicts the fundamental theorem of arithmetic unless a is equal to b is equal to 0, but b is not equal to 0 by assumption. And we have got a contradiction. Hence, we get a contradiction. Does that make sense? So it's just as simple as this. There's prime powers occurring over here that aren't the same prime powers occurring over here. If these two things were the same, they would since this is an inequality of integers, right? They have to have the same prime powers, the same prime factors, the same prime powers. Okay? So that's nonsense. Okay? The only way that this could happen if this was like 3 to the 0, which would make this one, and that would make this thing to the 0 as well, which would make this one. We can't have that case either because we assume that b was not equal to 0. B was not equal to 0 because we had a fraction, right? You can't have a 0 in the fraction of a denominator. All right, does that make sense? Okay, so that's what we have. Okay, so with the remaining class time, I want you guys to do some examples, and I'm going to come around and help you guys. So here are the examples that I want you guys to do. Let's do it here. So exercises. Okay, so from handout 2, we're going to do section 2, 4, 5, 11, section 3, 1, 2, and then section 4, all of them. Okay? So start with this one. Okay? And here, let me give you a hint to start on this one. X squared minus y squared is equal to x minus y times x plus y. Okay? So here, you're going to have this be, equal to 10, and then you're going to have two prime numbers, so 2 has to divide one of those things. Okay? That's the idea. Okay, and so I'm going to come around and help you guys now.